the second annual Rock Star Parade, our 3-minute introduction. We have one change. Unfortunately, Randy's not going to be able to present, but I have it on good authority that Gabe and several other faculty members are going to come down and do interpretive dance. So we'll have a 3-minute interpretive dance parade, and then we'll pick up with Diego. The format should be familiar to most of you guys that were here last week. But again, it's 3 minutes to do whatever you want. The slides that you sent are timed. They're in this order, which was chosen. There's a reason and a rhyme behind this order. It's in the order that people email me. There's no clear theme. There will be a 20-second break after each, and the idea of the 20-second break is just to sort of have a mind cleanse as the next speaker comes up, and so then you can give your full attention to the next person coming through. We'll go through most of the session today. We'll have a few minutes left for discussion if folks want. Next week, we have our first visiting speaker, and that's John Howell. Carrie, are you the host?
Yes. He's going to talk about virtual outcomes. Super cool.
Virtual outcomes.
Field geology in the 21st century.
So, our first speaker will be, a lot of you guys have animations. If you have animations, they'll work with the space bar or with the forward angle arrow as you go through the talk. So you can move through. If you press too many times, you'll advance to your next slide, and then you'll just be eating up into your own time as well. So can't go backwards. There's no going back. All right. Ready?
Yes.
First speaker. Ready? Go.
Okay, so I'm Sarah Lambert. I want first to do a big up to Paul and Noel for organizing that, because I think it's a great initiative. Sadly, I missed the first part last week. I was in Europe, and no, I won't think. So I won't sing. So I'm the newest faculty, I think, in the department still. I arrived a year and a half ago, and I spent this time setting up an experimental petrology. So for those who want to see it, it's on the 4th floor of this building. And so what we are doing in our group, called Magma X for Magma and Mantle Experimental Petrology, is reproducing the condition inside the Earth. Trying to find the timing here. Reproducing the condition inside the Earth, so at very high pressure, so up to 100 kilometer depth, and at temperature up to 1600 degrees C. And so we are a small group member so far, but we are growing up. So Otto actually started 2 weeks ago and is a master student in our group. Will and Sarah, sorry the names truncated, but Will and Sarah are Europe scholar who work with me in my lab. So Will actually finished his senior thesis this last semester, and Sarah just joined the lab this summer. And hopefully we will have a couple of new members by the fall 2020. In terms of themes, I don't know where is the time. In terms of themes, the big question we are interested in are anything related to magma genesis and magma transport, so how they form in the mantle, what kind of lithologies are melting, how they travel deep from the mantle, from deep in the mantle to the surface, how the oceanic floor is formed, so all these typical questions. And finally, one word about teaching. So since I arrived at university of Utah, I taught mineralogy and igneous and metamorphic petrology. And I'm proud that I reintroduced optical mineralogy in these 2 classes. So we have actually updated the full collection of scene section for these 2 courses. And so students will have the chance to have a brand new set of scene sections starting this semester, so I'm happy about that. One thing I want to mention to conclude is, if you want to follow the activity of the lab, I have a Twitter handle. And this coming week, I'm going to be part of the organizing committee of the Min Cup 2019. It's, some of you actually participated to the U edition last semester for the petrology class. But it's basically a competition where we vote daily for our favorite minerals, and it's a very fun thing to do. We launch the competition on Sunday, so if you want to have a look, go at Mineral Cup, and that's
So I'm going to take a few extra seconds, I guess. I'm a geological engineer and hydrologist. Most of my research ends up focusing somewhat on groundwater. Part of the reason I'm interested in that is that it's the largest volume of unfrozen fresh water on Earth, and most of the groundwater that we use goes to feed ourselves. So if we think about trying to have a sustainable world where we're feeding 8, 9, 10 billion people, we have to learn how to use groundwater. One of the challenges here is that the storage volumes are really large, but the fluxes into and out of groundwater systems are not large. That's what you need to know to figure out what the sustainable yield of a system is, but it turns out that that's the hardest thing to measure. So sort of the focus of much of my research is to make use of concepts of mean transit time. And it's in its most simple form, this is just the storage volume divided by the flux. So we're using geologic concepts to look at the storage volume. And then into the lab, here's Will Mace operating our, what he's helped build, one of the most automated noble gas mass spectrometers in the world, to try to estimate groundwater ages. And then from that, arrive at fluxes into and out of systems. Just a few examples. This is Olivia Miller on the Greenland ice sheet, collecting a noble gas sample. 10 meters below the surface of the ice, there's more than 140 gigatons of liquid water that stays there year-round. And it's moving through the ice with the same physics that it moves through aquifers. So we've been studying that. It probably discharges into crevasses on the fringes of the glacier, and possibly makes its way to the base, lubricating and accelerating the mass loss. One of the problems is that we need to go back and study that more. Closer to home, this is Nora Nilsson. She and some of my former students at the U.S. Geological Survey have been studying the Moab Spanish Valley aquifer. We've used a whole bunch of stable and radioactive tracers to arrive at a conclusion that the current recharge to that system is about equal to the current volume of water that's being extracted from it. So there isn't any additional developable water down there. That has a lot of people kind of upset in Moab. Kendall Fitzgerald is studying the Salt Lake Valley aquifer. In about a month, she'll present her thesis, so you should come and see that. And finally, Eric Humphreys and most recently Jens Ammon and of course Will Mace, who can do anything, are studying recharge in the High Plains aquifer and groundwater surface water interactions. Remarkably, just 30 centimeters below the bottom of this stream, you can find groundwater that's between 100 and 1,000 years old. I think it's kind of amazing. I'm going to end with one comment. Last week, Gabe was up here singing and dancing at the end of his sabbatical. I'm going on sabbatical in January, so maybe next year I'll be singing and dancing.
Okay, so I'm not going to sing, thank God, but I'm going to run through something more specific about my research group. I'm not going to talk about our Great Salt Lake stuff. Instead, I'm going to talk about particle transport. That's me doing paleomagnetic stratigraphy when I was doing my master's thesis way back when. And this is Mohammed Khan, who was my protector. This was in Pakistan. And while I was there, I made some other friends. And they got me interested in particle transport in forest movement. And what you need to know about that is that as a population of bacteria or particles moves through sand or gravel, for each layer of grains, you remove a fraction called eta of the population. And as you move through layers and layers and layers of grains, you have compounded loss that results in the concentration of particles decreasing about linearly with distance. That's true, though, if they're oppositely charged. And those are conditions favorable for attachment. In the environment, that's not the case. All surfaces tend to be negatively charged, they repel, and so you get these non-log linear decreases that make it impossible to predict how far things get in the environment. And so when we go to the pore scale, to the grain scale, to understand this better, we model the forces and torques acting on particles, and we determine whether or not they attach. And they will not attach if there's repulsion. So what we have to do is invoke heterogeneity at the nanoscale, which we know exists, but it's hard to get at. And so we paint surfaces with different sizes of clusters of heterogeneity, different surface densities, and we find that colloids or particles can either attach very quickly or very, very slowly. And when we upscale those, that is when we compound those, we actually, these curves emerge from that information at the pore scale. We actually get these non-log linear profiles, but only if we assume that these fast attaching particles aren't replenished during transport. And that's an unconventional assumption. So we've developed this hypothesis that incomplete mixing at the pore scale actually prevents that replenishment. And tracer studies show, if you represent the tracer in black and pure water in white, the invasion of that black water isn't complete, right? There's incomplete mixing that creates fingers. And the zones of incomplete mixing actually propagate from the rear sides of these grains. And that's where we see the simulations put all the particles that don't attach. So we're looking at those pore scale simulations to understand what's happening at larger scales and in the field. So I like to also take other people out to exotic places and to see if they get sick, which most of them do, actually. And so this is in Ecuador, mining impacted streams that we studied there. This is us crossing the Nangaritza River in an unconventional way, hanging out by a waterfall. And then last June, I took Owen Kahn, Sam Carter, Richie Torney, and Kerry Marshall from Geography up to the Himalayas of India, and we sampled water supplies in small villages and monasteries up there and had a great time. And found that it was really hard to sleep at 14,200 feet, actually. So that's it.
Well, what do Roman concrete, ancient Roman concrete, and very young Circe tuff have in common? Well, they all have glass particles that react to produce highly durable mineral cements. At the markets of Trajan, the glass scoria has a very highly potassic low silica composition. In marine piers and breakwaters, the pumice has a highly sodic and potassic composition. And at Circe, volcano in Iceland, basaltic glass alters in a very young hydrothermal system. All of these materials produce zeolite and calcium aluminum silicate hydrate cements that are very durable. We are studying these materials so we can begin to develop innovative research pathways for creating extremely durable concrete infrastructure that is also environmentally friendly. We can look at volcanic glass compositions in terms of their sodic and potassic compositions and silica, aluminum. We can look at mineral cement compositions in terms of their host glasses and cementing systems. And we can also make maps of cementing microstructures using beamline science. This helps us understand the mineralogical properties of these systems so that we can potentially use Roman principles to recreate them. And that's a new project that's beginning in October. Self-sustaining cementitious systems in Roman reactive glass concretes. This is a DOE ARPA-E program in which we're making pumice from foamed glass produced from recycled glass by an industry partner and tailoring specific compositions and nanoseeds. The goal is to enhance the reactivity of this interfacial zone of the particle so that it grows new mineral cements, increasing chemical and mechanical resistance. We're also further developing a novel bending test for looking at fracture processes in cementitious materials. This is an interdisciplinary collaboration with National Lab and industry partners as well as individuals in geology and geophysics, civil engineering, mechanical engineering, and material science. And you too can contribute. All you need to do is drink a beer at GeoSlice and recycle the bottle.
Okay, interpretive dance time.
Isn't Mark Lowen gonna give this one?
Yeah. So Gabe, this is your chance. One more encore performance. Okay, Dave.
Okay. Okay. This little guy is as hot as the sun, and they are the stars in our lab. They dwell happily in our two collectors and our new triple quad. We can measure with them strontium, boron, lead, uranium, magnesium, and lithium isotopes. We can do trace elements and elemental ratios, and we can characterize environmental processes. And also, we can use them for provenance and forensic studies. We can also do geochronology, we can do laser ablation, zircons, and uranium, thorium for lead, for carbonate, sorry. And then, so we operate as a recharge center. We reach hundreds of PIs and students from many institutions, just 25 academic units at the U. We run 5,000 to 10,000 samples a year, and I'm really proud to say that about 2/3 of those are run by undergrad that have put 20,000 hours of work in the last 10 years. Examples, some examples. So two guys with an impressive boat winning too many fishing competitions in Utah. They show the largest bass in Lake Powell. A detective, Utah wildlife investigator, confiscate the fish because somebody says, hey, those look like Quail Creek bass. So obviously fishermen know their fish very well. So we measure the otolith. This is a caught fish, the confiscated fish. And of course, we have 20 standard deviations to convince the judge that those are not from Lake Powell. If you want to characterize the whole basin, you need a lot more otolith. They were already the other one were just 10. Since we knew that this Nushagak basin contains 7 distinct isotopic zones, we could measure all this otolith to say which of those were more productive year to year for 2 species. We could illustrate this shifting habitat mosaic ecological concept that is related to long-term stability of productivity. Last one. So contamination history in our valley. This is a sediment core from Farmington Bay after railroad, transportation, and commercial mining. The enrichment factor went a factor of 20 up, peaking in 1919. And then this is the concentration. These are the isotopes. We tell us about sources. So the radiogenic lead, pre-industrial lead, got moved into Galenas from Park City, Pinkham District.
I'm not sure how this relates to me. I'm Margie Chan, and I started getting interested in a lot of the wonderful landscapes of southern Utah probably before many of you might have even been born. But I was kind of fascinated by why sandstones are different colors, and then what that had to do with some of these things that we call concretions, and you've seen some examples that are out in the lobby. And just sort of serendipitously from studying these, and Brenda Bowen was actually working with me a number of years ago along with Bill Perry. We started thinking about some of these concretions, and just serendipitously, the rovers on Mars landed and sent back some pictures. showing the similarities, and we could actually then start using some of our work to show the analogs between Earth and Mars. And even though a lot of this happened a while ago, 2004, it's been surprising that there's still been a lot of interest in using different Utah examples. Even some of this soft sediment deformation is now shown to occur on Mars. So sedimentary analogs from Earth to Mars is one thing I'm interested in. I'm also interested in astrobiology, which is the study of all of the living universe, and it covers kind of all these different aspects that you see here. And as I started looking at some of these concretions, I started thinking more about the fact that almost all of these things that involve water, way back in geologic time, since the Precambrian, have also probably involved microbes. And so when we are actually looking for extraterrestrial life, I think it's hard to know what a habitable planet would look like if it didn't have any life, because Earth is so heavily biased by life. So this is our planet, a water planet, and all we have is this n=1, and sometimes it is very difficult to project back what would a habitable planet look like without life. And so in every kind of mineral precipitate, whether it's something like this little speleothem that's starting in a cave in Hawaii, that is full of microbial life, to I think even the concretions that we see, those have also got evidence of life, even though it's hard to detect. Cyber technology is another thing I'm interested in, and Casey Duncan has been helping me with building a program so we can digitally collect field data, and that you can actually use that as your field notebook. I think that is very much the way of the future, so that's using cyber technology for earth science. And then the last thing that I'm very interested in is geoheritage, and the idea that we should be ethical in our sampling and in our science. We should leave no trace. This happened down by the Moab Fault, and they still wonder who did it. I would say as we're doing our field work, we are representatives of not only the university, but of our profession. And it's really important that we not trespass, or that we don't do things without permits. And this is becoming a much more important topic globally as people are looking at the idea of geoheritage and preserving the diversity of our planet. So that's all I have.
My name is Alex. I've been in the department since 2001, and I started as a student and continued as a postdoc. Now I'm a research professor, and all this time I was doing all this stuff, working for the consortium of electromagnetic modeling and inversion here in the department. And what we do there is we work with electromagnetic and potential field geophysical data, modeling, inverting, and interpreting. There are all kinds of applications where this data is used. It can be used to study deep earth, it can be used in exploration, environmental, civic, and even defense applications. Director of our consortium been since 1995 is Professor Michael Zhdanov. You might know him if you've taken his classes in Geophysics and inversion theory. And the funding provided for our consortium is from industrial and academic groups. So what exactly we do? We take geophysical data and we try to reconstruct the physical properties of the subsurface based on this data. We invert the data to get the properties. In this example, we reconstructed the density distribution and electrical resistivity distribution of the subsurface at below Yellowstone, and we defined this couple of bodies which have low density and low resistivity. And here on the left I have the cartoon which our seismology friends produced, which shows the plummet under the Yellowstone magmatic systems, and they also show a couple of bodies with partial melt, and the liquid material would show those properties which we saw in our images. And this is another example. This is an exploration example where we inverted the data from offshore Louisiana. Here we have some magnetotelluric stations here shown on top of the bathymetry, and the data has been collected and inverted for the electrical resistivity distribution to produce this image. And this body here shown in blue may represent a salt body which would have a higher resistivity than the surrounding. So in this case we were able to interpret this salt body which exploring for oil in this case. And it's not all fun and games. Sometimes we have to do some hard math, and this is the current project which I'm working on. I'm trying to solve these differential equations and Maxwell equations on the tetrahedral grid for plane wave excitation. And this would allow me to know the field anywhere inside this model or some other model. And the reason for using tetrahedral cells, it makes it easier to model some complex structures. The standard approach is to use just the brick cells, and it's very difficult to model a model like that with the bricks. But with tetrahedral, it makes it easier to discretize, but at the same time, it makes it very hard to solve. Thank you.
So I'm Holly Gladzy. I'm going to go ahead and get started. I'm a little bit of an anomaly in this department in that I don't currently do research, but I did at one point in time, and so that's why I'm here. When I started here, I came from the University of Michigan, where I had done a lot of work on the lacustrine barbed sediments to learn about the paleoclimatology of the region. Here, when I came to the University of Utah, I was working with Marge Chan and Paul Jewell, and we started a project that had two interesting components, looking at Lake Bonneville. We looked at a lot of the shorelines of Lake Bonneville, and we also went out and looked at the deep lake sediments there to determine the geochronology of the different lake levels of the shoreline in order to tie that back to climate. This is a closed basin lake. It's a really great indicator of how climate was changing over the last 15,000 years. But the second component of that was researching ways that we could actually preserve these Lake Bonneville special features. That's a sketch by G.K. Gilbert, who Paul Jewell showed a picture of last week. He was a geologist in the 1800s who came out and spent a lot of time in Utah and loved these features. So my second hat is now Director of Student Success and Teacher Development at the Center for Science and Math Education. In my role there, I do just about everything concerning science except for maybe science itself. So I work with students, I work with teachers, I work with the community, and now I'm working with the administration. And so I say we now, because it's not just me, it's a team of people. What we do over there is we develop courses such as a science communication course and a course in scientific inquiry. We have a learning assistance program, which is a little bit like TAs for undergraduates. We have an internship program. We have a new STEM degree that is for transfer students. We're working on an undergraduate research initiative over there. Many of you have been involved in the Masters of Science for Secondary School Teachers programs. That is something that we're very involved with. This is a picture of our latest cohort of Earth Science teachers, which we're very excited about. They're out of Antelope Island. And more. Finally, what I'm doing right now is I am a faculty fellow for the Senior Vice President for Academic Affairs, Dan Reed, and I am coordinating this Educational Futures Task Force. The job of that task force is to figure out how to accommodate growth in the student body to about 40,000 students, because we know it's coming, whether we're ready for it or not. We have a task force of about 70 different people in 6 working groups that are looking at all of these different areas of how to deal with that kind of growth. And that information is feeding back into the academic affairs arm of the entire University of Utah strategy refresh. And so I've kind of gone from looking at sort of very detailed scientific things to thinking about science more broadly, and now I'm kind of looking at the educational experience as a whole.
I'll be up in a minute. I remember different take. If you were to contrast my title with Howie's, I say get out there. So Howie's bringing stuff around in the university, the programs she talked about. The background slide is an open pit mine in South America. That's the focus of my interest, not the specific mine, but do collaborative research with people in geology, exploration, geochemistry, structure, international programs, geophysics, and everywhere you can make partnerships. So due to a request by students, a worldwide survey of getting out to see type localities, SEG, Study Economic Geology, set up a program, and my colleague William Chavez and I initiated the first program to take students worldwide, completely funded, anywhere I want to go for 10 days or so to learn about the geology, the culture, the methods. And we take vice presidents along, CEOs, industry consultants, geophysicists, some of our alumni that are in these higher echelons that have a story for students. Our trips typically have 16 students, 4 mentors, and 2 faculty, at least 2 faculty, the 2 leaders, and then maybe some from other universities, about 17 other universities. They can had students from 45 different countries and 17 states. And we get out there and talk about all different aspects. This in Chile, the mine is an engineering farms, all female. So we see different cultures in different countries, language groups, the obligatory breakfast. This trip was to the pyrite belt in southern Spain. And you can see there's a lot of pyrite. That leads to a lot of interesting aspects to the type of groundwater that is there. It's very acid. We see innovative 22nd century mining techniques. So we're looking to the future, go to places that you won't hear about for another decade in the general literature because they're way out there. Get up to 17,000 feet to 4,000 feet below sea level, 32,000 feet of vertical gain in the day. You can see the students are truly engaged. Nobody told them to smile. We're having a blast. We're visiting a museum that has meteorites from the Atacama Desert and so forth, but lots of other things like sapphires. Primarily, we frequently look at cores, which is 100% outcrop. So you can see diversity of materials there. A lot of individual instruction, a lot of expertise by the faculty and people that are involved. And as well as local field trips, various courses like mineral deposits, geology of Utah, mineralogy, etc. Some of our local trips to Yellowstone and platinum deposits. We've hosted lots of groups from France. Here they're participating in a symposium that we did, the annual department poster session, from Aachen, from Freiburg, from Munich, from ETH, from Columbia, and we do the last picture. These are Europe and undergraduate research projects, a whole bunch of those, some aspects of mineral deposits. But the last one, we're the inaugural team that's going to start the Michael J. Fitzgerald mapping course, and the same strategy. Anybody in the world to participate, graduate students, and that's where we go.
Hi, I'm Carrie Johnson. I am in the business of interpreting ancient landscapes and thinking about how and why they change through time. I use a variety of basin analysis techniques to do that. In theory, we would like to think of sedimentary basins as the ultimate sink in our sediment routing system from source to sink. And we go to sleep at night praying that they are faithful recorders of, at least at a first order, major signals and controls on that are acting on this entire system. So I don't have a song, but I will entertain audience participation if you cooperate. When you think about first order controls on sedimentary basin fill, just what are the primary signals that you would hope to be preserved in the sedimentary record? What sorts of things come to mind? On the count of 3, shout it out. 1, 2, 3. Tectonics. And where's my group? Sea level, you guys. Climate tectonics and use to sea. That's kind of the holy trinity. A trend in the field, though, is towards a more sophisticated view of how and if those signals are really propagated and preserved, and we talk about signal shredding, partly thanks to autogenics. So this refers to the natural self-organization behavior of depositional systems. Rivers avulse across their floodplain, they do that naturally. Delta lobes switch back and forth. You don't have to perturb the system to make that happen, but external controls can make that happen. And so what we talk about now is the idea of signal shredding, which is that these other factors can obliterate completely, in some cases, these original signals. We are dealing with the rock record, meaning that half of our puzzle pieces are basically missing. And so we're kind of left with this. And that is a very bleak view of modern basin analysis. Now that I think about it. So on the positive side, we have a lot of smart people tackling these kinds of questions. So my group addresses these problems from mainly a modeling perspective, but modeling broadly defined. We work on conceptual models of decades-old sediment in Lake Powell river deltas. We work in deep time and petroleum systems modeling. We create digital outcrop models using a drone in South Africa and in Utah. We do a lot of work in source-to-sink modeling using provenance techniques, and that includes the old standard detrital zircon, uranium lead geochronology, working in Diego's lab for that. But we're also starting to do some work on common lead isotopes and tetridyl potassium feldspars to put into the mix. Pete mentioned last time that we're moving back to Mongolia, yay, so there will be some new Asian tectonic models coming into play as well. The sum of all this is that we work all over the world on rocks of lots of different ages. Undergrads, there's room at the table. If you would like to get involved, please come talk to me. I'm going to leave my remarks.
All right, I guess I am next, not Dave. So I'm an earthquake seismologist. I have a research faculty appointment in the department, and I'm also on the staff of the University of Utah Seismograph Stations, or UUSS. So I'm mostly going to talk about the seismograph stations today for two reasons. First, I'm the only one from the seismograph stations who's giving one of these presentations. And secondly, a big part of my job is basically providing technical and scientific support for the seismic network operations. So this is the seismic network on the left. There's a key and some numbers over on the right. The upper right is the UUSS mission statement, reducing the risk from earthquakes in Utah through research, education, and public service. We're funded to monitor the two regions shown by the dotted black boxes on the left, Yellowstone region and the Utah region. So basically, what good is seismic network data besides producing seismicity maps like the one on the left? Well, seismic networks provide, including the UUSS network, provide data for at least 8 different applications that I could think of. The first is quickly and accurately informing the public and emergency responders after significant earthquakes. The initial information is from automatic data processing at UUSS. This is promptly reviewed and corrected as needed. Secondly, determining locations and rates of earthquakes for hazard analyses, especially in the magnitude 5.5 to 6 3/4 range. Why this range? Well, these are earthquakes that are big enough to be potentially damaging, but they're not quite big enough to cause surface displacement that's large enough to be preserved for a long time. Okay, the third was engineering ground motions for, or ground motion studies for engineering design. You can use small earthquakes for that as well, because you can use those to test models for predicting ground motions from larger earthquakes like the Bora Peak earthquake on the left. Identifying and characterizing man-made seismic events, including explosions, seismicity induced by mining and fluid injections, research on earthquake source processes, determining subsurface velocity structure, volcano monitoring up in Yellowstone. Volcanic eruptions are a lot more predictable than earthquakes. Finally, earthquake early warning, which will probably come to Utah at some point in the future. So I personally worked on 6 out of these 8 items. I've also done some work with GPS data and some work on high-resolution imaging the Great Salt Lake Fault with seismic reflection data. And Dave will probably talk about that.
Well, I taught my 21st success in geology field camp this 40 students. This is the group from a couple of years ago standing high up in the Raft River Range, about 7,500 feet, and beyond them is an exquisite fold that they get to map, created actually by Miocene extension. I also teach geology at Utah since Ron Brune retired 7 years ago, which I have cunningly reinvented as a de facto prerequisite for the capstone sequence. I teach a section of living with earthquakes and volcanoes every year, and I also taught the inaugural installment of the new Wasatch in the field. For about the same length of time that I've been teaching that course, I've been studying paleoseismology of faults submerged beneath Utah Lake and beneath the Great Salt Lake. These green faults all rupture in direct relationship to ruptures in the Provo segment. So they're auxiliary faults, just like the West Valley faults are to the Wasatch, to the Salt Lake City segment. There are some nasty things out in Utah Lake. Everything in pink here, well, the two large ones in the north and the east there, those are two massive debris flows. This one was 17 meters thick when it reached the lake, having crossed American Fork. And this shows that we can also get event horizons out of this data. It turns out that there are the equivalent of colluvial wedges associated with many of the events. It turns out that the entire bottom of the lake liquefies periodically. And this is just the uppermost of a stack of these earthquake-triggered debris flows that cut across the valley. And it turns out that even auxiliary faults have auxiliary faults that help in defining the event horizons. That was the map for Utah Lake. That's the most recent one, but we did the same thing, Jim Peschman and I, for the Great Salt Lake, the same type of data where we were able to accurately locate and identify event horizons on the Antelope segment, the Fremont segment, the Promontory segment, and the Carrington Fault is further northerly segment up, we call the Roselle segment up to the north, and we cored those event horizons on the Fremont and Antelope segments and dated them using radiocarbon techniques. So we were able to establish the recurrence interval of surface rupturing earthquakes on those segments that way. Thanks.
Okay, what do? I'm John Bowman, first of all. I'm a mix of a metamorphic petrologist and isotope geochemist. I've taught here a long time courses in introductory geology and undergraduate and graduate courses in petrology and geochemistry, occasionally thermodynamics, and I'm going to teach a thermodynamics course this spring, so sign up for it. It'll be wonderful. My research centers on crustal metamorphism and hydrothermal systems, processes of water-rock interaction, and timescales of these systems. They use a variety of tools ranging from field observations to in situ ion microprobe analyses of isotope and trace element compositions. And using these tools, we've done some interesting research. A few years ago, we actually evaluated the evolution of Archean crust in the Superior Province in Canada by looking at compositional and textural zoning in single zircon crystals, and that's what one of those was, which had an igneous core and a younger metamorphic rim around it. Okay. I have a lifelong or career project on contact metamorphic processes in the Alta stock, and we're using that as a natural lab to establish the thermal structure, which says that the oil is too big for the stock. There's been a lot of fluid infiltration, as indicated by extreme O18 depletions in the surrounding marbles here. That leaves a lot of big questions that I'm really excited to answer here. One of them is, we're already here, what are the heat and fluid sources that create such a big oil here? And John Bartley and Mike Stearns and Carl Benow and I are trying to answer these questions here. Also, since this is up here, there's no coherent start of metamorphism in the Altamira. There's no coherent talcosphere. So there's bedding controlled nature here of the talc and lack of talc in that area here. Okay, finally I wanted to say a few things about what my graduate students are. So another big question is, what are the mechanisms and kinetics of forsterite nucleation in the Altamira? Forsterite's a major mineral. These are high-resolution photographs of single olivine crystals that have been dissolved out of the marbles here, and you can see what incredibly complicated shapes they have to start out with. This is with increasing textural maturity. Carl Benno is trying to understand this as part of his dissertation research. And the other big question is what are the timescales of contact metamorphism? And there are new developments to be able to date this directly, including the dating of scar and garnet. And these are the initial results that Carl and Mike got in Diego's laboratory here. It's a Terra-Wasserberg plot. I won't go into any details. Just to say this is a very promising result here. You can ask some questions about it as well. So that's some of the research that I do.
Anybody else want to get up since we have 5 minutes left? All right. Well, thanks for all the speakers, both last week and this week. I think it was a lot of fun to see what we're doing. I would encourage everyone in the audience to contact the DLS organizers for subsequent semesters. What I saw were 25 presentations, of which all of them, everyone come up could give a great DLS seminar here. Just the fact that we get a little snippet, that no one feels like they could tell everything they wanted to tell of the story on what they were doing in 3 minutes. But they all tried and hopefully captivated the attention. I learned a lot, hopefully everybody else did as well. We'll start off next week with our first visiting speaker. Thanks.